Hello, welcome to section 1.8, which is on Introduction to Linear Transformations. This is the last section that we will cover in chapter 1, and it's really just a new perspective of the same types of things, so just another interpretation. So, in the past, we talked about a matrix equation of the form AX equals B in the context of systems of equations. But now we are going to think of it as a matrix A acting on or transforming the vector. So the result is vector B. So we're still solving this equation, but what we're doing is we're finding all the vectors x that are transformed into vector b when A acts on them. And this is called a transformation. So we have this fancy notation here, and I think the book gives a good description of it. But a couple things about this. Rn is the domain, and Rm is referred to as the codomain. And it's a rule that assigns each vector in this space to a vector t of x in this space. Sometimes we will denote matrix transformation as using this notation here. Okay, so it's the same thing, just different notation. So this example here talks about a linear transformation, and the thing you want to remember is that matrix A is the transformation vector of these. Okay, so we're going to first start with vector v and vector u, and we're going to use A to manipulate it. Okay, so let's start with vector v. Vector v is here with the coordinates 2, 1. So what I can do is find A times v and when I multiply these matrices, I get 4, 2, which is here. The same thing occurs when you try to transform vector u as well. So A times vector u is equal to -5, -1, which is here. Okay. So the range of T is the set of all linear combinations of the columns of A, because each image of the transformation is of the form AX. So this is shown to you down here. So this is our first example, and we are going to do a few things with this example. So we have 4 different matrices here, A, U, B, and C. And we define the transformation here. So again, domain, codomain. So T of x is equal to AX, which is shown here. So if T of x is equal to AX, then this is matrix A, this is matrix X. Here, when we combine those, we end up getting this. Okay, so this is all given to you. Okay, so there are 4 questions that we're going to answer. Here are 2 of the questions that we're going to answer. Part A says find T of u, the image of u under transformation t. Okay, so t of u is found by taking a of u, basically. So a times u. So this, and u, sorry, we don't have it here, u is 2, -1. So when we solve this, we end up with, so remember we multiply these, so this is, or actually you can use this formula. Let's do that. So remember this here represents x1 and x2, so we'll have 2 minus 3 times -1, 3 times 2 plus 5 times -1, just using these formulas, and then -2 plus 7 times -1. So this is equal to 5, 1, -9. So this is t of u. Now in part B it says find an x in R2 whose image under t is b. Okay, so there's kind of a lot going on here. So what we're going to do is first set this up, and we need to understand what exactly this is saying. And basically this is saying that t of x is equal to b for some x. Okay, well, what does that mean? Basically, what that means is ax is equal to b. So in our case, when we set this up, we have ax is equal to b. And b is given to us on the previous slide, which is this. So we're going to use the method from section 1.4 to solve this. And in order to solve this, what we'll do is we'll set up our augmented matrix. And we'll row reduce to solve. I don't have a lot of space here, and I apologize for that. So what I'm going to do is just kind of wave my hands a little and reduce row echelon form is the following. Sorry, this is messy. So this tells us that x1 is equal to 1.5 and x2 is equal to -0.5. So we can conclude that x is equal to 1.5 -0.5. And that would be the answer to part B. There are two other parts that we're going to address in this question. The next one is there more than one x whose image under T is B? This type of question is a uniqueness question. So is x unique or not? So sometimes there is more than one x. However, in this case, there is not. So the result from the previous problem indicated that there was only one unique solution. So there is exactly one x whose image is B. So you can say the result from part B indicated there is one unique solution. So there is exactly one x whose image is B. And that answers that question. Okay, and then for part D, it says determine if C is in the range of the transformation. This is an existence problem. So we want to know if there exists a C in the range of this transformation. So, one thing I forgot to mention is the reason we know this up here is there are no free variables. That might be helpful to know. Okay, sorry about that. Part D. So this is what part D is asking. So we want to find out if C equals T x for some x. So in other words, we want to see if AX is equal to C. Okay, so let's set this up. When we set this up, you may notice that it is very, very, very similar to part B. However, the only difference is the last entry. So I'm just going to set my augmented matrix up right away, where this is A, and then C is the column 3, 2, 5. So the only difference from part B is this last entry. Okay, as I have before, I'm going to wave my hand and bring you to the following reduced matrix. Okay, now once we analyze this, we can see we have a little bit of a problem going on down here. This row implies that 0 equals -35, which is not true. So this tells us we have an inconsistent system. Oops. So if we have an inconsistent system, we can conclude that C is not in the range of T. And that concludes part D. In this section, you will see information regarding shear transformation. And, you know, it may be helpful for you to kind of read through this, but overall it's pretty straightforward. So basically, if you start off with A, then this transformation in the same space is defined as T of x is equal to AX. So it's just this shear transformation. So basically, we go from this matrix, or from this image to this image. And the thing to point out is that the base remains the same. The bottom is fixed, but the square, it's the top of the square is if it's pushed to the right. So that part is moved. Here is basically an example. So we can say the image of this point, or of this vector, is 0, 2. And when we manipulate this, so this is A, this is U, and we end up with this new vector. Or if this is U, or V, or whatever, and we multiply this, then we end up with this vector. So it's the same thing. Matrix A is manipulating that other vector. Okay, so if you sketch some pictures of this, you can see what happens. Or I believe they're in the book as well. Linear transformations. So a couple things to mention. Linear transformations, they preserve the operations of vector addition and scalar multiplication. So we'll say that a transformation is linear if these two things hold. So the vector addition and scalar multiplication. A lot of this is pretty straightforward. It's just more of the same. Okay, so you can take a moment to read through this. More about this. Every matrix transformation is a linear transformation. So, you know, you can read through this too. I don't know that you need me to read it to you. So let's look at an example because I think that will be helpful. So it says, define a linear transformation in the following way. And this transformation is given to us. And we want to find these images. So we basically want to find T of U, T of V, and T of U plus V. So the first thing we're going to do is find T of vector U. So we're just using this formula here. So we're going to use AX, so this, and this is X1, X2, so 4 and 1. And then I can really just use this formula. So I'm basically negating 1 and putting 4 down here. It's pretty straightforward. So same thing with vector V. Here's A, here is V. Applying the formula, I get -3 and 2. And then finally, same thing. But now we are going to use matrix 6, 4 to get the following. And there you have it. This section really isn't too terrible. Enjoy.